Okay? I mean, we're going to do optimization after the test. All right? So what I'll ask you to do is, after you take the test next week, make sure that you kind of go back through that optimization and come in ready that next day. So next Wednesday, make sure that you are prepared for that section. I went even further. I made what I would consider to be a review, but it's not a real review. Hold on. It's just a list of problems out of the book that you can look at, okay? That's all it is. I'm not promising you anything, all right, about like, oh, the questions are going to be just like the questions he... This is really just problems out of the chapter review. That's all it is. Problems out of the chapter review.
Knowing how to solve.
If I were a student in this class and I were trying to get ready for a test that covers a couple of chapters, I'd probably go look at chapter review problems. And so what I've done is I've listed them for you. I've told you where they are. That's it. All right? You still need to review your homework. You still need to review the problems done in lecture. But here they are.
So once again, for your videos or whatever,
yeah.
For your class, they're a day ahead of us, right?
Y'all are pretty close. I mean, let's see. No, actually, you were ahead of them.
Really?
Yes, because we're going to do something today that I'm going to do with them tomorrow. Yeah, but in their class yesterday, I did 2 more graphing problems. And those problems actually were easier than the ones I did in here. But I told you that you should watch their class video just so you can see kind of a variation. And one of the problems that I did for them yesterday is very similar to number 3 on the take-home. Everyone have the take-home? Have a copy? Does anyone need a copy of it? Everyone's got it? All right. All right, so here's the review. Let's talk about this in a little while, not right now. All right, put it away. There are 2 things that I want to cover today. All right, and I'm going to do them quick, and I hope that as I do them, you'll see that these concepts are not like earth-shattering. It's not like curve sketching where we can spend 50 minutes on one problem. All right, these are pretty quick. Now the concepts, though, are very important in mathematics. So let's start here by talking about the mean value theorem. And I do plan on doing some review today, all right? Because our test is it Wednesday? Oh, it's Wednesday. Why did I think it was?
Yeah, because that's why I was wondering when we said be prepared on Wednesday
Oh, okay. Well,
be the next one.
Wednesday or
I'm not going to change the test, but that means Monday we're going to have more time, right? So I don't know what we'll do. Maybe we'll review a little bit more. But that means we need to go through and talk about 4.2 and 4.6. We'll do that today, all right? We're going to do 4.2 and 4.6. And we're going to still push optimization off until after the test. All right, so let's talk about 4.2, which is the angry value theorem. The angry value theorem. No, the mean value theorem. And here mean means average, not mean people. All right, so this mean value theorem is really an important theorem in mathematics. And it's a very visual theorem. It's something I can show you. You can look at it and say, oh yeah, that makes sense. But it starts out, before you get to the mean value theorem, you start with what's called Rolle's theorem. R-O-L-L-E-S. Rolle's theorem. So let's suppose that you have a function, all right? And this function is continuous on a closed interval. That means you can draw it without picking up your pencil, and it actually exists at the 2 endpoints. So by having a closed interval right here, brackets on the A and the B, that means the 2 endpoints are defined, right? Let's also assume that this f function is differentiable on the inside. So on the inside of the function, it's differentiable. That means no corners, no cusps, no vertical tangents. It's okay if the derivative is 0, but the derivative has to exist. It has to be differentiable. Understand? All right? And then I want you to imagine that this function, the value at a is equal to the value at b. So let's take a look. I'm going to draw it. Let's say we have a, we have b. What is that last condition, f of a equals f of b? What does that mean? The y values have to be the same. So I'm going to just draw kind of a makeup function here. I'm going to say, let's say at a, here's the value, right? And then let's say at b, it would have to be the same thing. And in between there, as I have to be able to connect these two dots together with a continuous function. That means I can't pick up my pencil, right? So can you imagine all these different things I could do to connect those two together? I could do straight line, I could do curves, right? Just no cusps, no corners, no vertical tangents. So I'm just going to make one up here. Would that be okay? All right. Rolle's theorem says this. There must exist a number c somewhere on the inside of AB. That means there has to be some number in here. All right? Somewhere in here, there's a c question mark, such that the derivative at c is 0. Do you see a place where the derivative would be 0? At the top of this thing, right? Right up here, the derivative is 0. Yeah? But also notice that when we say 0, right, flat, that means we have a flat tangent line. Do you also see that that tangent line is parallel to the line connecting these two endpoints? And what is the slope of the line connecting these two endpoints? 0, because the y values were the same, right? So if I draw a line connecting these two, the slope would have to be 0. So Rolle's theorem says, if you have a continuous function on a closed interval, that it's differentiable on the inside, and the two endpoints have the same y value, that you're guaranteed a derivative, a point somewhere in here, c, I didn't label it here, c, so that the slope of the tangent line there is parallel to the line connecting these two endpoints. Or you could say the slope of the tangent line somewhere is 0. Y'all understand that? Can you think of any way I could draw it where that couldn't happen? No, you're not going to be able to, all right? Now, this is why you have to have the differentiability. Let me show you an example of a situation where if you didn't have that differentiability, you could have a problem or a cusp. Look at that right there. See that? Does Rolle's theorem work for that? It does not. You're never going to get a tangent line on this that runs parallel to the line connecting those two endpoints. But Rolle's theorem only works if you're differentiable everywhere in here. And at this point, I'm not differentiable. So it fails. How about a straight line? What about the function that's just a straight line connecting those two? Is there a point in here where the derivative is parallel, or the slope of the tangent line is parallel to this line? Where? At every point, right? Pick any point you want, and the slope of the tangent line would be 0 there, which would be parallel to this line, right? Could it happen more than one time? I mean, that obviously happened a bunch of times, right? But you could have something goes like this. So where would the slope of the tangent line be parallel to this line right here? Here, 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 right? You actually have 4 different places where the slope of the tangent line is 0. That's Rolle's theorem. Any questions? No? Sure? All right, mean value theorem is like an adapted version of Rolle's theorem. All we do for mean value theorem is we take this concept of Rolle's theorem. So this is the same picture I had here. Two endpoints, right? Draw a continuous curve, right? But mean value theorem says, look, let's allow ourselves to rotate it. In other words, let's allow ourselves to not require that the endpoints are the same, equal to each other. Now, let's draw a line connecting these two endpoints together. What's the slope of that line right there? It is positive, but can you tell me in terms of the functions? So go back, what is slope? Slope is defined to be rise over run. So can you tell me what the rise is? Isn't it this y-coordinate minus this y-coordinate? The difference in the y-coordinates? So couldn't I say that the slope of this line is f of b minus f of a, right? That's rise over what? The run, which is b minus a. There's a difference in the x-coordinates. If this x-coordinate is a and this x-coordinate is b, then this is b minus a. So does everyone agree that the slope of that line in black there is this? Yes? So if we just took Rolle's theorem and we just took Rolle's and we twisted it, right? Then what we're saying is there's some point in here, right? There's some point in here where the slope of the tangent line there should be parallel to this line, right? So what we're saying is somewhere in here at C, the derivative at C, right? That means the slope of this tangent line should be the same as this. They should be equal. And that's what the mean value theorem says. And I'm gonna just scroll back up. That's not very big here. Let me see if I can make this a little bigger.
Have we talked about this?
Pardon?
Have we talked about the mean value theorem?
No? Well, yes, I did mention it. Do you remember us talking about a problem where we had the two race cars? Did we talk about that? No? Okay. I don't know why that's not getting larger, but here's what it says. F prime of C equals f of b minus f of a over b minus a. That's the mean value theorem right there. And I'm going to draw the picture next to it just so we're all clear on what's happening here. This says, mean value theorem says, if you have a continuous function on a closed interval. Okay, so here's our function, closed interval from a to b. And this time, it does not matter that these are the same. Okay, these are different values. This is f of a. This value up here is f of b. Y'all see that? Then the mean value theorem says as long as you connect that together with a continuous function and the derivative exists, that means there's no cusps, no corners, no vertical tangents. So let me go ahead and connect these together. There has to exist, there must exist at least one place. Could be two, could be three, could be an infinite number of them, but there's got to be at least one place where what? Tell me in words.
Where the slope
Is parallel, right?
The slope of the tangent line is equal to the slope of the, what do we call the line connecting these 2 points? We call it a secant line. Okay, secant lines connect 2 points, tangent lines are at 1 point. So there has to exist someplace. Do y'all see it? Do y'all see it in here? Let me see. Let me draw this is my secant line, right? This blue line, whoa, what happened? This blue line is this, right? The slope of that blue line is this piece. The slope of that blue line is this. Somewhere in here, there's a C where the tangent line runs parallel. Is it right there? No. A little to the left of that, right? So I start moving to the left. Somewhere around in here, right? It's going to run parallel. Good enough? And that corresponds to some C in here. So there has to be at least one. Now, in this picture, is there more than one?
Yes.
It looks like there's another one, right? It looks like it would be somewhere around there, right? Somewhere around there. There'd be another one. So maybe I call this one C1 and C2. There's two C's that do it. Make sense? That's the mean value theorem. Now, the reason they call it the mean value theorem is this. The slope of this line right here, the slope of that line, is an average rate of change. Average rate of change. I think I can make it more clear to you if I give you an actual problem. Let's say we have time, and let's say we have distance here. So you're going to go for a drive. Okay, you get in your car, you start driving, and let's say after 2 hours, okay, that's this right here. This is time. Let's say after 2 hours, see, Nathan's driving. We've gone 170 miles.
Man, you drive slow.
So Nathan's gone 170 miles in 2 hours. What's the average speed?
Like 85.
85 miles an hour?
Oh, that's what you're saying, but he's got to hit that, right?
Yeah, so the average speed would be total rise over total run, right? The rise is 170 miles, the run is 2 hours. So if I look at the slope of that line, right, the slope of that line would be 85. Yes? So that average speed, somewhere in here, there's a tangent that runs parallel. That's your instantaneous speed. So the mean value theorem is saying that under the right conditions, at some point while you're driving, you must attain your average speed. So there's no way to go 170 miles in 2 hours and not, at some point in the trip, go 85 miles an hour. You had to, at some point, have gone your average speed. At some point, you must achieve your mean value, your average value. Make sense? Okay, that's the mean value theorem. Now, it might be, well, I'll show you a pretty cool application of this after we do just one problem. So let's take a look at a function. I'm just going to make one up here. Let's take f of x equals x cubed minus 4x squared. And let's look at that on the interval -1, 5. Nice polynomial function, closed interval. This is a continuous function, isn't it? What I'd like for us to do is verify the mean value theorem, which I will abbreviate MVT. Verify the mean value theorem. That means prove to me that there is a number somewhere in here, at least one, right? Where the slope of the tangent line will be equal to the slope of the secant line. Show me it happens. Prove to me it happens. Understand? All right, so let's make sure to verify the mean value theorem, we need to look at a couple things. First of all, is f continuous? Is f continuous on -1, 5? We have to have that. Yes? Because it's a polynomial, it's continuous everywhere. The next condition we have is that the derivative is good on the inside of this interval. So is the derivative, is f differentiable on the interior? Well, what's the derivative of this guy? Yeah, it's a polynomial again, isn't it? And those are nice functions. So that means the derivative is going to be good. It's not going to ever have a cusp or anything like that, because to have a cusp would mean that that derivative would have to be undefined somewhere. It's polynomial, so it's defined. It's great. Right? So I need those conditions. Right? Now, what I want to find all values of C such that f prime of C equals f of B minus f of A over B minus A. That's the mean value theorem. I need to now generate all those C values where the slope of the tangent line will be parallel to the slope of the secant line. What is it that we know here, though? In this formula, what is it that we're given? I know what B and A are, right? I know B is what? 5, and I know A is -1, so I can replace those, right? And I also know what F is. So I'm going to write this down. And we're working like left side equals right side. So I want to know where this is equal to f of 5 minus f of -1 over 5 minus -1. Y'all still with me? And I can actually figure out what f of 5 is. Oh, I should have picked some better numbers, huh? What is it? 5 goes in here. 5 goes in there. Ooh, is that just 25? It's 25. It's 25. You know how I did that so quick? I factored out an x squared. Like that. And then I squared 5 and subtracted 5 minus 4. It worked. Okay, 25. And then minus, what's f of -1? So I'll do the same thing. -1 here. You know what? It probably works just as good here, huh? What do you get there? -1 minus 4 is -5? You get -5. So minus -5 over what? 6. So 30 over 6? What? 5? Oh, you're giving me, oh, sorry. Okay, yes, 30 divided by 6 is 5. All right, it's a long night. All right, so the right-hand side of that is 5. We just got lucky on that it's that clean, because I made this problem up. I was hoping it would be a fraction or something. 5. Got it?
Okay.
Is that all right? I want to figure out what values of C would make that equation true. Now, what is the derivative at C? In other words, take this, take its derivative, and replace all the x's with c's. So what's the derivative of this? 3x squared minus 8x. Now replace all the x's with c's. So that would be 3c squared minus 8c equals 5. Do you see what I did? I just took the derivative and then replaced the x's with c's. Y'all are looking at me like I'm crazy. Is that all right? Or yeah?
So that's to find those points.
I'm trying to find those c's now. So this is the equation I have to solve. And that is a quadratic equation. So I'm going to solve it. So I'm going to bring everything over to one side. And why don't you go ahead and solve that? Start working that out. While you're working that out, I'm going to start getting the graph of this set up on the computer, and we're going to check it. So use your quadratic formula, unless it factors. If that factors, then I'm going to go play a lotto ticket today, because then I would have had two things happen, which I really... Is it really going to factor? It didn't? See, the original function was x cubed minus 4x squared. It is? It does? It was from -1 to 5. Let me know if you get an answer, anybody.
I mean, I have,
Decimals are fine.
what you want, that's
Oh, decimals are great, yes.
They're great.
I mean, for this problem, yes, you'll need a decimal. What did you get some?
I got the first one, which is -8.8.
I don't know about that. Anyone? Anyone?
It would have been super clean, but it was
First
off
one
by
is 3.19.
Okay, C is 3.19 approximately. Okay. Anyone else get that? Anyone else trying? Did you get it? Yes? Okay. Negative 0.52. All right. I know that doesn't come out that good, but can everyone see these are the two solutions? You can all solve a quadratic equation, right?
Yeah.
Okay. So if I come back to my picture, here I've actually graphed the function, all right? Which you wouldn't have to do this part, but this is just to verify it visually. If I go here are my two endpoints. If I connect them with the straight line, then what those two solutions are saying is that if I go out to C equals negative 0.52, which is really the x-coordinate, negative 0.52, like if this is negative 1, negative 0.52 is about right here. Come down and put the point on the graph. If I draw the tangent line there, it should run parallel to that black one. Does it look like it might?
Yeah.
It does look pretty good. So if I draw my tangent line, it should do that. And then also if I go out to 3.19, which would be somewhere around in here, and I draw the tangent line, it should run parallel. Now I can actually have the computer do that for me. Have it draw the tangent line wherever I want. So let me do that. So I'm going to place it at the value, the first one was negative 0.52?
That's a problem.
There it is. Okay, pretty good, huh? I mean, it's not perfect, but yes? You know what? I can't change the color of this. Thick? Did that help? Yeah, that helped a little bit, right? And then let me change it. The other one was 3.19? 3.13? Okay. There we go. All right? These are parallel. You think you can handle that?
Yep.
I plan on putting that on the test. So in the review for this test, notice I have it broken up into 5 different things. Anyone need this?
When you said in class problem, in class.
Okay, so look, numbers 1 through 7 are like, hey, go home and, on top of all your homework that you're going to review, take a look at these problems from the chapter review. And I broke them up kind of by topic. So like the first topic is differentiation of inverse trig functions, exponential logarithmic functions, and then also logarithmic differentiation. And I gave you a big set of problems that you could look at that cover those topics. And I say, hey, if you want to do some L'Hopital's rule problems, you can try these. But I will admit that the problems in the chapter review for L'Hopital's rule are not ideal. I mean, I like the problems out of the homework set better than this, but I was, again, giving you just a different variety of problems.
What's the difference?
They're just different. They didn't have a whole lot of the 0 to the 0 ones or infinity to the 0. I mean, there just weren't a bunch of, there wasn't a good variety in the chapter review. 3 is closed interval method. 4 is increasing, decreasing, and concavity problems. And then 5, these are mean value theorem problems. Those problems actually come from this section, numbers 9 through 12. And so I would suggest you look through those problems. All you do is you figure out what f of b minus f of a over b minus a is. That's going to be a number. And then you take the derivative on the other side and put c into it and then solve the equation, whatever that equation is. It may be a polynomial equation. It might be a rational equation. Could be a log equation. It just depends on the function. But for the test, I plan on keeping it within the level of problems that you see here. I'm not going to go crazy and give you some equation you've never seen before in your life.
Like square root.
Well, I don't remember what those 4 problems were. But all right, but you can ask me on Monday. If you have an issue on those problems, you can come in on Monday and we can talk about it. All right. Now, that's the mean value theorem. And here's another way we can use the mean value theorem, but I'm not actually going to test you on this, all right? But I want to show it to you. I need one from the book. So just because I said I'm not testing you doesn't mean just turn me off. Because you never know, I could ask a bonus question, right? I could, right? So look at this. I'm going to take this equation, x cubed minus 15x plus 4 equals 0. All right, that's an equation, isn't it?
Yeah.
Now, it's not a quadratic equation. It's a cubic equation, right? And if I asked you to solve that right now, you would have major problems solving that. You could try synthetic. It's not going to work. It just wouldn't. All right? So you would be stuck, and there would not be a way that you could solve that. So even in college algebra, the synthetic division was nice, but it didn't always work. So you'd be stuck. All right? What I want to do right now is I want us to show this equation has at most one root or solution, okay, however you want to look at it, on the interval -2, 2. Show me that thing has an answer, but only one answer between -2 and 2. So you're sitting here and you're like, well, how am I going to do that, right? That's kind of weird. This is not asking you for the solution. It's just saying, hey, show me it only has one answer in here. So the way we would do this is as follows. Let's take the left-hand side of this equation, since it's set equal to 0. Let's call that f of x. So I'm going to define a function, f of x equals x cubed minus 15x plus 4. And what I'm basically saying is, where are the x-intercepts of this graph? Right? That's what I'm saying? Where are the x-intercepts of this? Do y'all agree? Because if I said find the x-intercepts of this, what would you do? Set it equal to 0. So this is just the backwards statement of this. So I'm looking for the x-intercepts of this. But I'm only looking at it between -2 and 2. So if I were to start to try and graph right now, what would the value of this function be at these two endpoints? So let's plug in 2's easier. So let's go 2 in here. 8 minus 30, -22. What is it? -18. So we'd be down here at the point -2, -18, right? What would happen if, not -2, +2, -18. What happens if you plug in -2 into this? -2 cubed is -8 plus 30 plus 4. What's that? 34 minus 8.
30, that's 22 plus 4, 26.
26, okay. 26. So we'd be up here at the point -2, 26. Y'all got that?
Yeah.
Now, this is a continuous function, isn't it? And it must go from here to here, right?
Yeah.
Do you agree then that it has to pass through the x-axis for that to happen? There's no way I can draw that without crossing through the x-axis. So I'm going to have an x-intercept in here, right?
Yeah.
So we already know that a solution exists, doesn't it? Right?
Yeah.
Okay. We don't know what it is, but a solution exists. The key word in this problem is this. At most 1. Because what tells you that this thing doesn't come down, cross through, come back up, come back down, right? It could do that in here, couldn't it? How am I possibly going to show that this thing can only cross through here one time? So let's see if anyone can get it with, let me draw it crossing through more than once first. And then let me draw it crossing through only once. And let's see if anyone in here can tell me what the difference is between those graphs, like what it is that I can investigate to try and determine which of those it is. What about the tangent lines? You're on the right track. Okay. Ah, there you go. So look, if you're going to cross through more than once, right, then that means you're going to have to go down, 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 go past the x-intercept, and then come back up to get another one, right? So when you make that turn, what happens to your derivative? It goes from, here it would be what? Negative. It would have to flatten out to 0, then turn positive, then turn back to 0, then go negative again, right? But if you only cross through one time, at least with the one I drew here, what happens? My derivative is always negative. So maybe just looking at the derivative and saying, hey, maybe the derivative stays negative the whole time. Maybe I can show that it's negative the whole time, and that would be enough, right? If I tell you go from here to here, and your derivative is always negative, that means you're going down the whole time, which means you could never turn back up, which means you can only cross once. Make sense? Critical idea there. So let's take a look at the derivative of this. The derivative of that function f is what? 3x squared. Is that what you said? Minus 15. All right, so that's it right there. And, well, is that always negative? Not always, is it? It's not always negative. However, if I graphed the derivative, this is a parabola that opens up, isn't it? And we moved it down 15. So down here at 15, negative 15, I know this parabola opens up, right? Remember what we're looking at here. This is the graph of our original function. This is the derivative. I was interested in asking the question, is my derivative always negative? Well, it's not. This is not always negative. But if you look at this in a picture, it is negative sometimes, isn't it? It's below the x-axis here. That means negative. Out here, it's positive. So the question would be, where are these? Because anywhere between here and here, my derivative is negative. So what are these points right here? Set that to 0. So if I set this to 0, where's the derivative 0? I get 3x squared equals 15, and then x squared is 5. Square root, right? Plus or minus root 5. So root 5 here and negative root 5 here. That's not root 5. Well, what do you think? That's these numbers right here, root 5 and negative root 5, are actually bigger, right? Root 5 is out here. Negative root 5 is out here. So if I look between just negative 2 and 2, as long as I'm in here, the derivative, right? The derivative here is negative. So when I'm between here and here, the derivative is negative, which means it's always decreasing, which means it cannot come back up and get another x-intercept. Make sense? How would you say this? Exactly what I'm doing is how you say this. You look at this, you show that there's a change from a positive value to a negative value, you investigate the derivative, and then we make a conclusion like this. Since no change in the, not concavity, no change in the increase, decrease. So since f prime of x is negative on negative 2, 2. So this is after I've drawn my picture and convinced myself of that. Since the derivative is negative on negative 2, 2, f can only have one x-intercept on negative 2, 2. Which is the same as me saying that the original equation can only have one solution, right? Because x-intercept is the solution, it's a root. Yes?
Probably nothing, but you use brackets there on the interval.
It wouldn't matter.
It wouldn't matter.
It wouldn't matter. Because I could say since f prime is negative on negative root 5 to root 5, there I couldn't use the brackets though.
Well, I just know on the original problem you used parentheses.
Yeah.
in the interval. I just didn't know if that made a difference.
Nope. All right. Now, in my college algebra classes, when I teach college algebra, I don't mention something to my college algebra classes, and I'm curious if you were taught this or told this. Something about, like if you have this polynomial, do they talk about the number of turns that you could have? Anyone's college algebra teacher talk about the number of turns?
Actually, mine was like old school. Like he taught us similar to like that little graph. So it's going up, going down.
Uh-huh. So how many turns can you have in this?
Is it 3?
You could have 3 turns? How do you determine that?
The largest one going, right?
Is that what you're told? 3 turns?
It's been a while.
Okay, it's been a while. Does anyone remember it clearly? No? At most 3 turns? I don't think that's it. I think it's 2. It's 1 less than the power. 1 less than the power. Why?
Because the derivative.
Because the derivative of that would be what? A quadratic, right? And so you come back and you're saying, okay, how many turns could this have? Well, turns would require a change in the derivative from going up and down, right? The derivative of that is a quadratic. How many times can the quadratic change signs from negative to positive? Only twice, right? In 2 places. You can only have 2 places where that happens. Right? It went from positive to negative back to positive. But you're not going to have more than 2 because this is a quadratic. It can only have 2 solutions. If this was a 5th degree polynomial, you could have at most 4 turns because the derivative of that would be a 4th degree polynomial. It could have at most 4. Does that make sense? Yes. Okay. All right. Well, I don't talk about it in my college algebra classes because it really, at the end of the day, doesn't make that much of a difference. Once we get here, we're doing it anyway. We're figuring out what it looks like. So, all right, let's move on. One last thing on mean value theorem. This problem I didn't use mean value theorem at all, did I? No. But this problem is in that section. I don't assign it for homework, but it's in that section because I'm leading you up to the next section we're about to do. But there was one last problem, and it has to do with the car race. And we didn't talk about the car race?
I don't think so.
Okay, well, we'll have to discuss the car race right now. This is a top view of a race, and we have 2 cars. We have Nathan and Bailey racing.
As long as I win,
Okay? Those are your cars.
I don't look up close.
All right, so they're going to race down this track. And here's the finish line. And here's all I'm going to tell you, is that we start the race, they both take off. And when they come to the finish line, it's a tie. Perfect theoretical tie. I understand it would be impossible to figure out if it was perfect, but this is theoretical. So they come to the end, neither of them win. Nathan's car got a little longer, but whatever. So they tie at the end.
What happened to my bumper?
Well, you hit something out there, I guess. All right? So listen to the questions I'm about to ask you. First question. Well, maybe I'll just take you right to the question.
Take your time.
You have to pay attention the way I say it, though. Is there a point in time, somewhere in the race, where they're both going the same speed?
Yes.
At the same point in time?
Yes.
Guaranteed?
Yes. Oh, at the
It
same.
doesn't have to, right?
That's the question. I'm asking you.
They have to reach a certain speed, though. Like,
I feel like they have to.
Not at the same time.
Not at the
Yeah.
same time.
Not at the
Because then
same
when
time?
we both get to the end, then it's the average, which means they both have to be doing something at the same time, at the same point.
I want everyone to have an opinion.
the average is the same, but you can be like, you can start off slower and then hopefully.
Let's make sure we all understand the question. Does anyone have a question on the question?
Can you restate the question?
I will restate the question. They start at the same place, they end at the same place, they tie. Is there a point in time where they're both going the same speed? And that point in time is the same point in time for both of them. That means if Nathan's driving, Bailey's driving, they're racing to the finish, is there some point in time where they both look at their speedometers and they go, shit, we're going the same speed at the same point in time?
Yes.
Now, I'm not talking about at the beginning, because at the beginning of the race, of course, they look down, they're both going 0. And I'm not talking about at the end. Somewhere in there, did they have to be going the same speed at the same point in time? Everyone understand that? Okay, we're going to take a vote. What do you think? No? Not guaranteed? You got to do better than that.
Yeah.
You think so? Okay. Take a stance. So you think so? Sounds it? Yes? Yes? So we have 3 yeses, 1 no.
Yes.
Yes? 4? Yes? 5? 6 yeses? Okay, now we should have done a blind vote.
Yes.
Yes? No? No?
You said
Yes?
Guaranteed, right? You said guaranteed.
Guaranteed.
Yeah.
Yep. Yes?
At the same point in time?
Same point in time.
Oh, wait.
No?
Can we switch?
Yeah, it has to be at the same point in time. That's what I'm saying. They're both driving, and then they both look down and go, crap, we're going the same speed at that exact instant. Anyone want to reconsider? Okay, we'll take a hand vote this time. I'll let you reconsider. You can change your answer. How many of you believe that that point in time is guaranteed? Yes, that will happen. So 1, 2, 3, 4, 5, 6, 7, 8. How many of you think that that will not happen? 1, 2, 3, 4, 5. Okay. And flip a coin, yes or no? Yes, okay. All right. So now, can somebody argue your case? Someone who said yes, can you argue your case?
It's just kind of, at some point, it may happen.
May, no, I'm saying it has to.
I
Guaranteed.
I think I can argue it.
You want to argue your yes? Okay.
So if they have a distance, a specific distance,
Mm-hmm.
and they both finish in the exact same amount of time, so at some point, the average, because from start to finish, that's the average, so at some point, they both had to be going the exact same.
That's good. So you're realizing that each one of these cars, so Nathan, as you went down, you had a distance, total distance.
I could have fluctuated speed, but we both had the same average speed.
You both had the same average speed, which means the mean value theorem says that somewhere in your trip, you went your average speed.
Yeah, so I
And
guess
somewhere
it's
in his trip, he went your average, the average speed also, which was the same. But was it at the same point in
then
time?
I guess no.
It's not guaranteed.
Not guaranteed.
Okay, so are you changing your vote now?
Well, the way, yeah.
Okay, so someone who's saying no, argue your case.
I argued your case already for now. I think, yeah, because I mean, you're covering the same distance, you arrive at the same time, right? So, like I said, you can be slower, but still, like, okay, I need to speed it up, but you still get at the same, theoretically, the same time, right? So you're not, I mean, it can just vary, so it's not guaranteed it can happen, but I don't think it will always happen.
Okay.
I guess you could use that too, though, because at some point you're having to catch up with the other person.
That's right, because you got a tie, right? You've got a tie at the end, so you can't always be behind, right? Okay, so look, the reason why I like to give this problem, because this is a good example of how wonderful mathematics is. Because we can get real world problems like this, where you can have an intuition, you can have a pretty good argument for your side, someone else can have a pretty good argument for their side, you can go back and forth all day long, and who's right? The math is going to be the right answer. So let's get to the right answer. You ready? I'll save it for the end. I'll let you know. All right, so here's what I'm going to do. What I'm going to do is very much what Nathan suggested I do. And that's, I'm going to graph this situation with two functions. So we're going to have time here, and we're going to have distance here. What we know about this is the following. If I draw Nathan's in red, he starts at 0, he starts here, he's gone nowhere, right? And at the end of his trip, he finishes at some distance, right? Some time has gone by and some distance. And in between there, it doesn't matter. I didn't tell you like how fast Nathan drove or how he drove. He just got from that point to that point, right? So I need to draw a curve that goes from here to here. My choice.
Shouldn't distance be speed?
No, I'm not graphing the speed. I'm graphing how far you went. So I'm just going to draw Nathan's like this. Okay, there he is. There, all right? As long as he didn't do some sort of like physical teletransportation where his car disappeared and reappeared, that should be a continuous function. It should also be differentiable because there's no way that your speed went from like positive to negative in an instant, right? You'd always have to slow down and then, like if you decided to drive, stop, and back up.
Speed's still not ever negative.
You can have negative speed. It's relative, right? If I throw a ball at you, I could say I'm throwing it at 20 miles per hour that way, and you could say it's coming at me at 20 miles per hour. So we have to establish relative, like to who, what's positive and negative. So, and then here comes Bailey, right? Bailey in his Ford Fiesta starts off a little slow, but at the end he picks it up, whatever, and they tie, all right? I have no problem with Ford Fiesta though. Okay. They're good cars, man. They're good cars. They're reliable. Right there. Now, I could have drawn this anyway. I could have had them crisscross, couldn't I? That's not important in this problem. How this happens is not important. I'm going to call this first function, just to use some notation that we've had in the past, I'm going to call this one f and this one g. So both f and g are continuous functions. Would you agree? They're both differentiable on the entire interval. And let's call this first point A. Let's call this last point little b. So the argument that Nathan had initially was that, hey, look, these both have the same secant line, don't they? Yeah. And that means that for the red curve, there's somewhere in here where I'm parallel to that. And for the blue one, there's somewhere in there where I'm parallel to that. But is it at the same place? It doesn't look like it has to be, does it? Now watch this. I'm going to create a new function. All right? Here's a new function I'm going to create. I'm going to call it h. Everyone, h is equal to f minus g. All right? I just came up with that out of nowhere. All right? Now, can you graph for me h? I'm not going to put it on top of that. I want to do is separate axes. But same thing, time here, distance here. What can you tell me about f minus g at the beginning? So what's the difference between these two functions at the beginning? 0. What is the difference between these two functions at the end? 0. Got it? Now, when I graph h, I have to connect these 2 points. Is this a continuous function, h? Yes, because it's the difference of 2 continuous functions. And back when we were studying continuity, that was one of the things we put up there. The difference between 2 continuous functions is still continuous. So now I have to draw this h function with a nice smooth curve and connect these 2. It doesn't matter how it happens, right? I have to connect them. What does Rolle's theorem tell us?
That at the derivative, 0 has to be
Somewhere in here, right? Let's say here, I'm making it up, C. Somewhere, the derivative is what? 0. Agreed? By Rolle's theorem. So I'm going to state that up here. By Rolle's theorem, we have that there exists a C such that what? The derivative of this function, which was which function? H, right? The derivative of h is what at that? Is 0, right? Because the slope of the secant line is 0, so the slope of the tangent line is 0. Agreed? Here's the awesome part. What is h prime of c? So go back and look at how we defined h. H was f minus g, right? Another way I could have written that was this. H of x equals f of x minus g of x, right? If I ask you right now to tell me what's the derivative of h, you would take the derivative on this side, right? Which would be h prime of x equals, what's the derivative of f minus the derivative of g? Well, you just take the derivative of each one individually because it's a sum or a difference, right? So the derivative of h should be the derivative of f minus the derivative of g. You still with me? All right, now plug c into this and tell me what you get. Plug in c. So this is the relationship between the derivatives of h, f, and g. But you know that there exists, by Rolle's theorem, there had to be some point where the derivative of h at c was 0. So plug c into this equation right here, and what do you get? H prime of c is what? 0. And then f prime of c, you don't know what that is, minus g prime of c. And you don't know what that is, do you?
So they're equal to each other.
Ah, but that means if I add the g prime to this side, right? I have g prime of c equals f prime of c. And what does that mean? That there's a point in time, c, where the derivative of both of them are parallel or the same. It's guaranteed. No argument. The math just showed it right there. There exists a point c that lives inside here. And that's another key thing here. Remember, Rolle's theorem says if you're going to go from here to here, that number c is inside AB. It's not at the edges, it's inside. So I just showed that there's some point in time here. I don't know what it is, okay? I can't tell you. But there's some point in time c that the slope of the tangent lines at that point on both functions, f and g, are parallel, which means that they had to be going the same speed. That's pretty cool. I mean, probably more to me than you, but how do you, I mean, that happens a lot in mathematics. That happens a lot in the real world. You can't sit there and be like, yeah, we're gonna build that bridge, and you know, what size I-beam are we gonna use? Just use that one. Looks good. You know, like, I mean, you have to have some mathematics behind it to, know it's gonna work.